So today we are going to start lecture number 7, I think, yes, of Math 120. In the previous lecture, we were discussing about determinants. How to find determinant of any matrix. Can you see the board clearly? Can you read it properly? Anyone? Just tell me, please.
Yes, sir. Yes, it is okay. It could be better.
It could be better. Let me.
तो contrast नहीं सही बहुत ज़्यादा ना white wash होया हुआ है सब कुछ.
So we have discussed how to find determinants in the previous lecture using finding determinants using cofactor expansions. I told you about how to write a cofactor expansion with respect to some row. So how do we write an expansion with respect to some particular row of that determinant? Expansions using any row to find the determinant. For example, if we have any general matrix, for example, A from 1, 1, A1 to so on, A1n, and A2, 1 to 2, so on to n, and so on, AN1, AN2, so on, ANn. So this is a general matrix. If we want to write a row expansion to find the determinant of A, then determinant of A is basically can be calculated by first row. If you want to write an expansion, cofactor expansion, with respect to first row, then what do you write here? You have to write A11, C11 plus A12, C12 plus so on until the last element of that row into the cofactor multiplied by a respective cofactor. I hope you know what is a cofactor. Now, this is a cofactor expansion with respect to the first row in order to find the determinant of A. Similarly, we can write other row expansions with respect to any other row. For example, maybe third row. If you want to write an expansion with respect to third row, then C31, C31 plus, A32 into C32 plus so on, plus the last one is A3n now and C3n. This will again give you the same value of the determinant of A. And in general, how can we write in a compact form, in a short form, if you want to write this one in a short form, we use the sigma notation, which is a sum notation. And which index is varying here? The second index, J index. Okay? This one, this one, this one, and this one, and this one. Okay? So we have to vary here. J is from 1 to n, summation. Sum of J from 1 to n. A1J, C1J. So this is basically, we have written here this cofactor expansion with respect to first row, which can be written in a short form or a compact form in this way. So now if you want to write this one in the same form, how do we write it? Summation J from 1 to n. Now, this is the first row. Now, which row is this? Third row. So we have to put here 3J, C3J, because the row is fixed. Here, the row was the first row. Here, we have the third row. So the ith index is fixed. Jth index will vary. I hope you get it. If you have any question, you can ask me. And in general, if we want to write cofactor expansion for any ith row, any row, then how do we write it? So in that case, determinant of A can be written, determinant of A is equal to sum j from 1 to n, A, ij, cij, where I is fixed. I could be 1, 2, 3, so on, n. So I will be fixed here. Only j will be. So this is in general formula, you can say, or expression for a cofactor expansion in order to find the determinant of matrix A. Similarly, we can write expansions using columns. We can find determinant by using cofactor expansion with respect to a particular column. If you have any questions regarding this thing, you can ask me, otherwise I'm going to erase it. And I'm going to write now cofactor expansion with respect to column. Now, for any particular column, the cofactor expansion, for example, with respect to the first column, how do we write the cofactor expansion? In this case now, row will vary. Number of rows are varying here, and the column is fixed. Okay, you can write cofactor expansion with respect to the first column, and you can find the determinant of A. How do we write it? A11 C11 plus A21 C21 plus so on plus AN1 CN1. Okay. Now you can notice here that the second index is fixed. J index is fixed, whereas the first index varies. So we can write it in this form: sum I from 1 to n, AI1 CI1. Because I represent the row index, so that's why we put I here. I from 1 to n, AI1 CI1. Okay, where so this is your determinant of E. And in general, for any column, for any particular column, you can write with cofactor expansion. And that, how can we write it? Summation I from 1 to n, Aij, Cij. Now, what is j? J is from 1 to so on n, where j is fixed now, because j represents the column. For any column, you have to put the corresponding index number here, and then you can write the expansion column, cofactor expansion with respect to any column in order to find the determinant. I hope you get it. If you have any question, you can ask me. Let's discuss an example of this thing before going to discuss the second method for finding determinants of any matrix. So this is the first thing we can know about it. Okay, the boards are not properly lined. Let me erase this thing. Let's do an example. Here. Now, let me have a matrix A, which is maybe 1, 2, 3, minus 1, 5, 7, 0, 0, 8, 9, 3, minus 5, and fourth one is 2, negative 7, 8, and 10.
सर अभी तक हमने adjoint नहीं किया ना matrix का?
Earlier, last time बताया था आपको what is adjoint. Adjoint is basically if you want to find, let's include it adjoint here as well. Find inverse of this matrix. How to find inverse, and then find determinant of this matrix. In the previous lecture, I told you how to find A inverse. For that, what you do, you have to compute. In order to find the value of A inverse, you have to compute all the cofactors of this matrix. What are the cofactors? Cofactors are, by definition, First we need to find the cofactors. Cofactors is what? Cij is equal to -1 raised power I plus j mij. And mij is what? Mij is a minor of that matrix. And how do we define it? Mij is what? Mij is a determinant of the same matrix A11. For example, चलिए यहाँ पे general definition क्या होती है? I can tell you in words. Mij is the determinant of a matrix obtained by deleting ith row and jth column of the given matrix. This was the definition of minor. So you calculate all the cofactors for this matrix, given matrix C11, C12, C13, C14, and then so on. The last one is C44. Okay, here you have C41. So this matrix is called C matrix, which is the matrix of cofactors. Now, A inverse is what? It is 1 over determinant of A times adjoint of A. Now, what is the adjoint of A? Adjoint of A is the transpose of the cofactor matrix. Once you can compute all these cofactors, you put them in a matrix, you get C. Now, take the transpose of C. This is what? This is your adjoint of A. Now, after computing determinant of A, you just put these two things here and you get the A inverse. This was basically the method in short. Now, let's come back to, I hope you can do it. You can see the previous lecture. I have explained how to compute these cofactors. You can see in that. Now, let's come back to the determinant, how to compute the determinant. In order to compute the determinant, we have to select any row or any column about which we have to write a cofactor expansion. Now, I would try to be a little, you can say, by looking at the rows and columns, I would see which row or column will make it for me to easily compute the determinant. So you can see that there are 2 zeros in the second row. Okay, there are 2 zeros in the second row. So I would prefer to write cofactor expansion with respect to second row in order to compute the determinant. So what is the cofactor expansion with respect to second row? It is basically A to 1, C to 1 plus A to 2, C to 2 plus A to 3, C to 3 plus A to 4, C to 4. Why I prefer to write a cofactor expansion with respect to second row? Because you can see that this third and fourth entry are already 0. So this factor and this factor, they will be 0, obviously, because the coefficient, that element is 0 here. So we don't need to compute these cofactors. So you have to act wisely in order to select any row or any column. So now I'm going to write A21. A21 is 5, and the cofactor 21. Cofactor 21 is -1 raised power 2 plus 1 times the minor of 21. Minor of 21 means second row, first column. You delete these two things and write the remaining entries in the determinant. 2, 3, -1, and then 9, 3, -5, -7, 8, 10. So this is the minor, 2, 1. Now, plus second entry is 7. And now you again write the minus C to 1. Sorry, I have to write here -1 raised power 2 plus 2. Okay, so according to the definition of cofactor, so 7 times -1 raised power 2 plus 2 times minor. Now you are going to delete second column and second row, and the rest of entries will be 1, 3, -1, 8, 3, -5, and 2, 8, and 10. So these are your minors. Now, in order to compute this matrix, sorry, determinant, because it's still a 3 by 3 matrix, so we don't have any direct method for finding determinant of this matrix. We again apply a cofactor expansion on this matrix, on this determinant. Okay, we can do separately as well. You can say this as determinant of maybe B, and you can say this as determinant of C. You can find the values of determinant of B and C separately and then put them back here, their values, in order to get the determinant of A. You can work systematically. So now let's separately calculate these determinants. Determinant of B is what? Determinant of B is this thing. You have to select again any row or any column. So it's not mandatory or necessary that you choose the same rows and columns as you have chosen for finding the determinant of B. You can choose any other row or any column in order to expand this determinant. So I'm going to use first row, for example. So 2 times -1, 1 plus 1 minus. We are going to delete first row and first column, and we are left with 3, -5, 8, 10. Plus second entry, 3 into -1 raised power, first row, second column, times first row, second column, delete karenge. What do we get here? 9, -5, -7, and 10. Plus third entry into -1 raised power 1 plus 3. Now we are going to read first row and third column. First row and third column, we get 9, 3, -7, 8. Now we can solve these determinants. Okay, so it would be 2 plus 1 times 30 minus 40 plus 40. 30 minus 40. So this is 70. Plus 3 into, this is -1, so we'll have a negative sign here. And here we have 90 and minus 35. 90 minus 35 is what? 65? No, 55. Okay, 55 plus minus 1, this one, and then here 72 minus 20, 72 plus 21. So you get the determinant as 140, negative 165, negative 3, and 9. So you simplify this and you get the value of this determinant of B. You put this value here. Now you compute again determinant of C and put the value of determinant of C here. You simplify all these things and you get the answer. You get the determinant of this 4 cross 4 matrix. So this is basically the procedure of finding determinant of any matrix of any order. So first of all, we write a cofactor expansion with respect to any row or any column. We get a 3 by 3, and then again, in order to solve 3 by 3, we have to write again the cofactor expansion until we get a 2 by 2 matrix. Okay, we'll write the cofactor expansions for each subsequent determinant until we get a minor of 2 by 2, which can easily be then solved. So this is what all the process is in order to find the determinant of any matrix. If you have any question, you can ask me. If you have any question, you can ask.
सर तो अगर 4x4 मैट्रिक्स आ जाए माइनर में तो आपको उसका 2 दफा फिर से डिटरमिनेंट लेना पड़ेगा.
बिल्कुल, डेफिनेटली. अगर आपके पास यहाँ पे 5 by 5 मैट्रिक्स है, आपने उसका डिटरमिनेंट फाइंड करना है, then you have to write successively many cofactor expansions. पहले आपके पास minus 4 by 4 का आएगा, फिर आपके पास minus 3 by 3 के आएंगे, फिर आपके पास minus 2 by 2 के आएंगे. So until you get minus of a 2 by 2 matrix, you have to write down the cofactor expansions for each determinant. It's a very lengthy process. In fact, no one uses this one currently, but it's in your syllabus. You have to follow this method.
Sir?
Ji.
Sir, to find a determinant by cofactors, the matrix need to be a square matrix, or we can find a determinant of a rectangular matrix too.
You tell me, is it possible?
I think no.
Why is it not possible? We can find determinant of rectangular matrices. Yes or no?
No.
हाँ, काफी दफा मैंने पहले भी बताया है कि इनवर्स किसी भी रेक्टेंगुलर मैट्रिक्स का पॉसिबल नहीं है फाइंड करना. You can only find inverse of a square matrix. In order to find the inverse of a square matrix, you have to find the determinant. So determinant is also obviously possible only for the square matrices, not for rectangular matrices. Okay?
Yeah.
Okay, that's good. Now we are going to discuss a more applicable method, a more convenient method in order to find the determinant of any matrix, which is basically using elementary row operations. Row operations. I hope you know what are the elementary row operations. We have used these elementary row operations while solving linear systems. So can anyone tell me how many elementary row operations we can apply in order to solve a linear system?
3.
Yes, 3. But here, while finding, in order to find the determinant of a matrix, those 3 elementary row operations, they would be changed slightly here, because we are not dealing with the linear systems now. We are dealing now with the matrices. In a linear system, for example, if you have 2x plus 3y plus 9z is equal to 2 and many other equations. In linear systems, if we interchange any 2 equations, there will be no change in the solution of that linear system. This was basically one of the elementary row operation. The first elementary row operation was what? Row I can be interchanged with any row j. This was the first elementary row operation. And the resulting augmented matrix or resulting linear system will not change because these 2 linear systems are equivalent. We talked about the equivalent linear systems. Their solution will remain same by applying this elementary row operation, by interchanging any 2 rows of that augmented matrix. Nothing will change. Because in linear systems, if you change 2 equations, interchange 2 equations, nothing will change with respect to the solution of linear systems. Okay? Solutions of those 2 linear systems will remain same. But in determinants, if you interchange any 2 rows of determinant, then the determinant of new matrix after interchanging any 2 rows, the determinant of new matrix will be equal to the negative sign of the determinant of previous matrix. Okay, so the first elementary row operation is now slightly changed. You cannot use those elementary row operations which we were using while solving linear systems. In determinants, these elementary row operations will slightly change. When you interchanged any 2 rows of a determinant, the new determinant which you obtain, its sign will be changed. Okay, so you have to change the sign of the new determinant. Clear? Any confusion? Second, now in determinant, in linear systems, the second elementary row operation was what? We can multiply any row with any constant. Okay, this was the second elementary row operations in linear equations. For example, in linear equations, maybe 4 is equal to 5. We can multiply this equation on both sides with any constant. We multiply this by 3, for example. What do we obtain? 6x plus 9y plus 12z is equal to 15. So nothing will change. This equation is exactly same as the previous equation when we apply a constant on both sides of the equation. So the resulting equation or the resulting linear system will have same solution as of the previous linear system. So it was allowed, we can multiply any row of the augmented matrix with any constant. But here in determinants, we are not dealing with the equations now. Okay. Now you have to look at this. Now, whenever you multiply a determinant of any matrix A with some constant, for example, determinant of C times A. Now, आपने क्या किया? Determinant A को C से multiply करें, ठीक है? Not this one. Any certain row से आपने multiply किया, and you obtain a new matrix determinant of B. You multiply the determinant of A of any row of A. यहाँ पे row से करते हैं. You multiply any row of A with some constant. Then the resulting determinant will change. Then you have to compensate that constant also. If you multiply that constant with any row and obtain the determinant of B, then you have to compensate that constant and you have to multiply it. So you have to divide it outside that matrix.
Sir, यहाँ पे जो आप 1/c into determinant of A कर रहे हैं, आपने C को A matrix से multiply किया था, right?
No, not CA matrix. Any one row of that determinant of A.
हाँ जी, ठीक है. मतलब A से किया था ना, B से तो नहीं किया.
नहीं, आपने A की किसी एक रो को किसी C से multiply किया. So you have to compensate that constant as well. You have to divide it outside.
हाँ जी सर, लेकिन ये obviously तब होएगा जब हम उसी specific row को use कर रहे हैं cofactor expansion में. अगर हम किसी और row को use कर रहे हैं तब तो नहीं हम C को compensate करेंगे.
Let me tell you one more thing. There's a property of determinant.
Camera focus में नहीं है.
We'll discuss it later on in detail. If we have a determinant of some matrix, A11, A12, A13, A21, A22, A23, and A31, A32, A33. Okay. Now, if you multiply any row of this determinant, for example, I'm going to multiply this row with some constant C. Okay, only this row. Then this is what? This is equal to C times A11, A12, A13, A21, A22, A23, and A31, A32, and A33. Okay. So this is a property of a determinant. Okay, you can take common any constant from any particular row from a determinant of a matrix. So this thing is different from this. C times A is what? It is you have to multiply C with every entry of A. Now this is a matrix. Matrix scalar multiplication is different from the scalar multiplication of determinants. Now what does this mean? C times A. It is C A11, C A12, C A13, C A21, C A22, C A33, and C A31, C 3, 2, and CA, 3, 3. This is what we mean here, C times A. But C times determinant of A is not equal to C times A. Remember this. Okay, whenever you multiply a constant with a matrix, then you have to multiply that constant with each entry of that matrix. Whereas in determinants, this is different. Determinant, when you multiply determinant of C times A whole determinant is what? It is Cn determinant of A. If A is a matrix of order n, अगर यहाँ पे ये matrix लेंगे 3 by 3 का, तो यहाँ पे C क्या आ जाएगा? C की power 3. Because you are taking common C from each row. From first row, you took C common 1C. From second row, you took common C, you get another C. From third row, you took common C, you get another C. So they are 3 C's. So you get C power 3 times determinant of A. I hope you get it.
सर एक चीज कंफ्यूजिंग है थोड़ी सर हमने आपने जो पहली वाली एग्जांपल दी है उसमें आपने सिर्फ रो 2 से सी को मल्टीप्लाई किया है लेकिन आपने जो बाहर फिर कॉमन ले लिया है वो पूरे मैट्रिक्स के साथ मल्टीप्लाई हो रहा है सी
Yes. That is not a matrix, that is determinant.
अच्छा you're talking about determinant ऊपर
ठीक है ऊपर वाला determinant है यहाँ पे matrix है C times A is a matrix. Now this is different operation. C times A is means that you are multiplying C with each entry. यहाँ पे C times determinant of this is what? C might be multiplied with only first row or only second row or only third row. Okay.
सर इसी वजह से ना कि जब आप इसकी कोफैक्टर एक्सपेंशन करोगे डिटरमिनेंट्स लगाने के लिए तो C हर जगह मल्टीप्लाई कहीं ना कहीं तो होएगा ही होएगा इधर में तो C कॉमन ले सकते हो
Definitely.
So now it makes sense.
So these two things are different. I hope you get it. Now, whenever you apply the second elementary row operation is what? Whenever you multiply any row of that determinant, C times row I, for example, then determinant of B is what? 1 over C times determinant of A. You have to compensate that constant outside. Okay, you got my point? So this is the second elementary row operation. Now we are going to discuss the third elementary row operation. What was third elementary row operation in linear systems?
Addition.
क्या था?
Adding a multiple of a row to another row.
addition या
Multiply any row, you can multiply any row with any constant and add it to some other row, and that row will be changed, Rj. Okay, this was the third elementary row operation. So this remains same for the determinant as well. Okay, there will be no change in the resulting determinant of a new matrix. Okay, so this will remain same. Only these two are slightly different in determinants as compared to the linear systems. Is there a question in the chat window? Let me see that. For this, will we use cofactors to find? No, we are not going to use cofactor expansions here anymore. Now we are going to use elementary row operations in order to find the determinant. We can use, but I'll tell you in the next example that we can use both at the same time. We can use combination of both methods in order to get determinant as quickly as possible. Okay. So let's
just use echelon forms. जो सबसे easy नहीं है technically.
Huh?
Echelon forms को use करना सबसे easy नहीं है.
Yes. Now, in order to find the determinant of any matrix, we are going to reduce that matrix into echelon form. Okay. For example, if we have this determinant, we have to find this one, 2, 1, 1, 3, -2, 0, -2, 1, 1. Okay. So I need to find the determinant of this matrix. What I'm going to do using elementary row operations, I'm going to make 1 here, okay, and then 0 below it. How can we make 1 here? I just have to divide it by 2. So 1 by 2 are 1. This will give me what? 1 here, 1 by 2, 1 by 2. So मैंने अंदर 2 से divide किया first row को. I have to multiply it outside. I have to compensate that constant outside that determinant. Now this is equal to this now. Okay. After applying this row operation, 1 by 2 are 1. Okay. 2 से divide किया है पहली row को, मैंने multiply करना बाहर. The rest will remain same. Now I'm going to make these 2 entries 0 in order to reduce this matrix into upper triangular matrix, or you have to reduce it into echelon form. Now, what operations do I need here? -3 R1 plus R2, and this will going to change R2. So this determinant is now what? 1 by 2, 1 by 2. Second row will be changed. So I get 0 here. And क्या करना है? -3 से multiply करके add करना है यहाँ पे. Okay. So -3 by 2, -2. This one I got here. फिर -3 से multiply करके add करना है यहाँ पे. So -3 by 2. Okay. So this one is what? Is -5 by 2? No, sorry, -7 by 2. So this is -7 by 2. Third row में भी हमने यहाँ पे 0 बनाना है. Another operation, we can apply multiple operations at the same step, but I would request or advise you to apply one operation at one step. So second operation.
-3 over 2 नहीं है? अच्छा.
Yeah.
हमने अच्छा नहीं 3 1 के साथ किए सही.
So now 2 times row 1 plus row 3. This is going to change row 3. Okay, this is the second operation. So we are going to multiply this with 2 and add it here. 0, 2 and add it here. 2, 2 से multiply करके add it here. 2. We get this. Okay. Now next step is what? We are going to make this one 1. Okay. In order to convert this matrix into echelon form. यहाँ पे कैसे 1 बनेगा? What operation do we need here?
Divide by -7 over 2.
2 by 7 -R2. Okay. So what do we obtain here? Equal to 2 times 7 by 2 negative. Okay. In order to compensate this constant, what we have to do? हमने यहाँ पे multiply कर रहे हैं second row को. तो हमने यहाँ पे divide भी करना है इसको बाहर. तो वो reciprocal हो जाएगा इसका. So it will be 1 by 2, 1 by 2, 0, 1, and -7 by 2, which is 21 by 4. Okay, and then 0, 2, 2. Now, what I have to do now, I have to make zeros below this entry. Okay. Now, what operation? Yes.
Sir, second row, third element, isn't it be? It would be -3 over 7 or +3 over 7, because we have to multiply -2 over 7 with -3 over 7.
Yes, thank you. So हमने -7 by 2 से multiply किया ना? Sorry, 2 by 7 से. तो 2 cancel हो गया, negative positive हो गया, तो ये 3 by 7 है. Yes, thanks. Now I'm going to make this one 0. So what do I need here? -2R2, -2R2 plus R3, and this will change R3. So this will become now 2 times -2 by 7 times determinant of this is 1, 1 by 2, 1 by 2, 0, 1, 3 by 7, and tell me these entries. So this will be 0, 0, and what is this entry? आप इसको -2 से मल्टीप्लाई करेंगे और इसमें ऐड करेंगे. So it will be 2 -6/7. ठीक है? तो ये 14
8 by 7.
8/7. 8/7 आ गया. So we get this. Now this matrix is in echelon form. We don't need to apply further operations. Now,
Determinant is initial form.
hello, D, any question? Now, you can see that here we have 2 -7/2 means 2 to cancel हो जाएगा, -7 आ जाएगा. So we get here -7 times 1, 1/2, 1/2, 0, 1, 3/7, and 0, 0, 8/7. Now you can use a cofactor expansion here in order to explain this determinant. I'm going to use the first column. Okay, I'm going to expand this determinant using cofactor expansion with respect to first column. What do we have here? -7, 1 times -1 power 1 plus 1 minor. First row, first column छोड़ दें. 1, 3/7, 0, 8/7. Plus second entry 0 है, वो 0 हो जाएगा. Plus third entry 0 है, वो भी 0 हो जाएगा. So what do you get here? -7. ये तो पहले से था. यहाँ पे क्या आया? 1. फिर यहाँ पे क्या आया? This into this minus this into this. It means 1 into 8/7. This. अब आपके पास 7 और 7 cancel हो गए और you get -8. This is your determinant. Now one thing which you notice here that what is this? This is the product of diagonal entries of this determinant. Okay. So once you have an upper triangular matrix, it's the value of this determinant is what? Is equal to the product of its diagonal entries. Okay. Once you reach at the echelon form here, then the determinant of this matrix is what? You don't need to expand this using cofactor expansion. This was just to show you that what is happening here. Now, this determinant of this matrix is what? Is the product of its diagonal entries. Now, by looking at or by observing this, we have a theorem. We have a very famous theorem, in fact, that the determinant of upper triangular matrix or lower triangular matrix, or you can say generally triangular matrix theorem. Determinant of triangular matrices. Triangular matrices, कौन-कौन से होते हैं? Anyone tell me?
Upper triangular and lower triangular.
And then diagonal matrix, scalar matrices. ठीक है, जिसमें एक diagonal element होता है, सिर्फ diagonal. So upper triangular, lower triangular, diagonal matrices, all of these matrices. This theorem is true for all triangular matrices. The determinant of triangular matrices is the product of matrix क्या है इसका? Matrix is the product of its diagonal entries. Okay. So that's why we are basically interested to convert the given determinant into echelon form. Echelon form means we are going to convert that matrix into upper triangular matrix. Once the matrix is in upper triangular matrix form, then the determinant of this matrix is what? The product of its diagonal entries. So we have also verified this by expanding this matrix using cofactor expansions. What did we get here? We get the product of its diagonal entries. I hope you get it. If you have any question, you can ask.
सर लेकिन डिटर्मिनेंट ही -8 नहीं आया.
लेकिन वो पहले के कॉन्स्टेंट थे ना जो हमने कंपनसेट किए थे, ठीक है?
जी जी.
They played a part in the value of determinant. But we are talking only about the determinant of this determinant. Okay?
Right.
Excluding these factors. Okay?
Right.
You got it?
जी जी.
Okay. Any other question? Now, whatever the order of determinant is now, you can find the determinant of that matrix, whatever the order is. For example, if you have 5 by 5 matrix, 10 by 10 matrix, you can use mixture of these two methods as well. Okay, you try to reduce that determinant into echelon form. Some steps you can do at certain step, you can do a cofactor expansion in order to simplify things, and then again you can reduce that matrix into echelon form, whatever is easiest or whatever is convenient, and of course whatever is fast to calculate the determinant. I hope you get it. If you have any question, you can ask. For example, this is an appropriate example for applying the two methods. For example, compute this determinant. 1, 3, 1, 2, 0, 1, 0, 0, 0, negative 1, 2, 2, negative 2, 1, 0, 1. Now, you look at this determinant and tell me, how would you like to find the determinant of this matrix? Anyone?
Reduce echelon forms, I think. Cofactor expansion is too lengthy, I think.
Again, if you ask me to find this determinant, I would first expand this matrix with respect to second column using cofactor expansion. क्या होगा? ये एलिमेंट है 1 आपका. First, second row or second column delete कर दें आप. What you get here? 1, negative 1 raised to power 2 plus 2 minus 1, 0, negative 1, 1, negative 2, 1, 2, 0, 1. ठीक है? मुझे आसान है cofactor expansion because एक एलिमेंट के लिए मैंने लिखा, आपका ऑर्डर जो है वो डिक्रीज हो गया. अब दोबारा अब मैं क्या करूंगा? अब अगर फर्ज करें यहाँ पे 0 नहीं होते, फॉर एग्जांपल यहाँ पे 0 नहीं है, देयर आर सम अदर नंबर्स, देन व्हाट वुड आई डू? अब ये फैक्टर तो खत्म हो गया ना आपके पास. एक ही स्टेप में विदाउट एनी एफर्ट आपको 4 by 4 डिटरमिनेंट 3 by 3 में आ गया. सो दिस इज मोर फास्ट, दिस इज फास्टर देन अप्लाइंग एनी एलिमेंट्री रो ऑपरेशन. So what I am going to do now, I'm going to apply elementary row operations on this determinant, which is a 3 cross 3 now. पहले क्या था? 4 cross 4 था. I have to make these 3 entries 0, then this one, फिर उसके नीचे 0, and this takes a lot of time. अब इसी एक स्टेप में आपका ऑर्डर जो है वो काफी डिक्रीज हो गया, एक ऑर्डर डिक्रीज हो गया। अब सेकंड में क्या करूंगा, मेरी मर्जी में इस पे एलिमेंट्री रो ऑपरेशन लगाना शुरू करूं, एक दो एलिमेंट्री रो ऑपरेशन लगाएं, दोबारा से आप कोफैक्टर एक्सपेंशन लगा दें। Which one, मतलब which one is convenient, which one is easy, you can use that thing. So अब यहाँ पे again I would not prefer to apply any elementary row operation because you can see again the second column has only one non-zero entry. So I would try to expand this determinant using second column. I have to write only one minor and then product and I get the determinant of that matrix. So
सर वैसे जब हम क्वेश्चन अटेम्प्ट कर रहे होंगे तो हम ये जो नई मैट्रिक्स है इसको कैसे रेफर करेंगे?
कौन सा नई मैट्रिक्स?
ये जो यानी कि जो अभी 3x3 बनी है,
this is minor, this is the minor.
पूरी
हाँ?
ये मैं कह रहा हूँ जो पूरी मैट्रिक्स हमें जो डिक्रीज ऑर्डर की बनी है, इसको हम क्वेश्चन में कैसे रेफर करेंगे कि ये डिटरमिनेंट, अब ये नई मैट्रिक्स को कोई नाम देते हैं?
नहीं, आप ये भी कह सकते हैं, you have to say here that in order to find the determinant of this matrix, I'm going to use a cofactor expansion with respect to second column. Then we obtain this. Okay.
जी जी, मैं कह रहा हूँ आप इसको जब करेंगे तो व्हाट आर वी सेइंग, हम किस पे लगा रहे हैं नई कोफैक्टर एक्सपेंशन सेकंड स्टेप पे?
इस पे आते हैं ना, again next step, again using cofactor expansion, again using cofactor expansion. You don't need to give it a name. You just have to apply the steps. You have to apply the procedure. Again using cofactor expansion. Huh?
इसका नाम ऐसे minor 2 नहीं होगा, M22?
That is basically minor 2. This determinant. Technically, if we say it. But you can say, after simplifying it, you can say it's a new matrix, a new determinant, in fact. This whole thing, after solving it, you can say it is a determinant of B because it's a new matrix, a new determinant. Okay, this is what? This is equal to this one. 1, 0, 0, 1, 1 minus 2, 1, 2, 0, 1. Now you have to apply further steps on this determinant. I hope you get it. If you have any confusion, you can ask.
Sir, with the element which we multiplied with it, would it like go on in the calculation? Like in this case, 1 minus 1. In this case, it is 1. But like if it's another constant, would it continue in this?
You have to take this constant along with all the calculations till the end. Okay.
Okay.
Sir? Yes, go ahead actually.
जी, yes.
अच्छा, so I was asking कि हम ऐसे कर सकते हैं कि शुरू में हम जो है reduce method से सिर्फ एक रो को चेंज करें और फिर उसके बाद cofactor यूज करना शुरू कर दें, ऐसे कर सकते हैं?
This is what I was talking about. You can apply any of these two methods at any time, at any stage.
Thank you.
Sir, why don't हम ये second column को लेके cofactor expansion नहीं कर सकते? वो भी easy होगा in M22.
Second column ये वाला?
नहीं, minor में से, minor का second column, क्योंकि इसको आपने elementary row operations लगाने हैं ना minor पे. अगर second row से कर ले cofactor.
मैं आपको कह रहा था, अब आपकी मर्जी, आपने इस पे elementary row operations लगाने हैं या again cofactor expansion लगानी है. This is up to you. You are the judge. You have to decide it. What you have to do. ठीक है? You have to find determinant as faster as possible. I hope you get it. If you have any other confusion, you can ask me. Otherwise, we are going to discuss properties of determinants. एक प्रॉपर्टी तो पहले मैंने अभी आपको बता दी है कि the scalar multiplication in determinants is different from the scalar multiplication from the usual matrices. I hope you get it. Determinant में हम जब किसी constant से multiply करते हैं तो either we can multiply with one single row or with one single column. Okay? ये column में भी possible है. उसी तरह कांस्टेंट बाय मतलब अगर आप कांस्टेंट से मल्टीप्लाई करेंगे तो कांस्टेंट से डिवाइड भी करना पड़ेगा टू अ सिंगल कॉलम और टू अ सिंगल रो. Okay. Now I hope you can find the determinant of any kind of matrix. Here's an exercise. Find the value of k. Find the value of k for which the matrix given below is invertible. So this is your matrix 1, 2, 4, 3, 1, 6, k, 3, 2. How can you find the value of k here? Anyone?
वैसे तो कोफैक्टर एक्सपेंशन भी कर सकते हैं रो 1 को लेके और उसके बाद हमने बस आई गेस इंश्योर करना है कि जीरो नहीं होगा.
आप यहाँ पे पहले इसको is for find the value of k for which the matrix is not invertible. ये करें. आप कैसे करेंगे? पहले वो क्वेश्चन बाद में आपसे पूछूंगा.
Determinant is equal to 0 put करके solve कर लो.
Yes.
That's the determinant of this matrix should be equal to 0. आप इसका determinant equal to 0 put करें, solve करें, determinant find करने की try करें. At the end you can get the value of k. अब अगर हम is invertible कह दें तो फिर क्या होगा? इसका determinant 0 नहीं होना चाहिए.
ये नहीं होगा जी.
ठीक है, आप इसका डिटरमिनेंट फाइंड करें, आखिर में k की टर्म्स में डिटरमिनेंट आएगा, उसको नॉट
इक्वल टू.
तो आपने बेसिकली बताना ये फाइंड कर लिया कि k किस वैल्यू के इक्वल नहीं है. ठीक है, तो आपको यू कैन ऑटोमेटिकली नो फॉर व्हाट वैल्यूज ऑफ k द गिवन मैट्रिक्स इज इनवर्टिबल. ठीक है,
So वैसे टेक्निकली हम इसको इस तरह भी तो कर सकते हैं कि हम इसको नॉन इन्वर्टिबल इमेजिन करके k की वैल्यू निकाल लें और बाकी जो भी वैल्यूज रह जाएंगी उन पे
other than those values you would say that the matrix would be invertible. So that's true. Okay, so you can do this question in these two ways.
Sir, web work upload होएगा over the weekend?
आज I shall upload another assignment for you related to inverses and determinants of matrices. First property, I already told you about the determinants. For example, अगर आपके पास किसी एक यहाँ पे CA11A, CA12, CA13 और यहाँ पे KA21, KA22, KA23 और यहाँ पे k के बाद आप p कर लें A31, A32, A33, p times p times. अगर ये डिटरमिनेंट है तो पहली रो में से आप c कॉमन ले लें, सेकंड रो में से आप k कॉमन ले लें एंड थर्ड रो में से आप p कॉमन ले लें. So you get A11, A12, A13, A21, A22, A23 and A31, A32, A33. So this is how it works. You can take common from each row and put it outside. Okay. So similarly, it works for the columns as well. Ab C, 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 K, 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 P, P, P kar dein, wo common le lein, we get again the same result. This is the first property. The second property is that second property, this is the first property. Second property is determinant of A transpose is equal to determinant of A. Whatever matrix you have, the determinant of transpose of any matrix is always equal to its determinant, okay, without transpose. This is the second property. For any square matrix, or you can say let A be a square matrix, if A has a 0 row or column, then its determinant is 0. ये क्यों भाई? Why this is so? अगर किसी भी मैट्रिक्स में कोई एक रो या कोई एक कॉलम 0 है तो उसका डिटरमिनेंट 0 होगा. क्यों?
उसके हर कोफैक्टर एक्सपेंशन के हर एलिमेंट के अंदर 0 आ जाएगा.
कोफैक्टर एक्सपेंशन उसकी उस रो के रिस्पेक्ट से करेंगे तो ऑब्वियसली सब कुछ 0 ही होगा. अच्छा, let A be another square matrix. If any two rows or columns are identical in a matrix, then its determinant is 0. क्यों? ये क्यों भाई?
सर क्योंकि फिर हम सिंपली एक रो से दूसरी रो को कैंसिल करके उसको 0 रो बना सकते हैं.
हाँ, डेफिनेटली इट्स बेसिकली स्पेशल केस ऑफ द अबव प्रॉपर्टी. अगर आपके पास कोई से दो रोज या कोई से दो कॉलम आइडेंटिकल हैं किसी भी डिटरमिनेंट में, तो आप एलिमेंट्री रो ऑपरेशन लगा के दूसरी रो को मतलब दोनों रोज को एक दूसरे में, अगर किसी एक रो को दूसरे में से माइनस कर दें, यू गेट अ 0 रो. सो 0 रो आ गई आपके पास, कोफैक्टर एक्सपेंशन करेंगे उस रो के रिस्पेक्ट से तो डिटरमिनेंट उसका 0 हो जाएगा. सो दीज आर बेसिकली some obvious results which you have to remember while solving. जी जी.
मतलब एलिमेंट्री रो ऑपरेशंस करके रोज को 0 कर रहे हैं तो कॉलम्स का क्या चक्कर है?
कॉलम को भी कर सकते हैं. क्यों? जो दूसरी प्रॉपर्टी है क्या ये रोज और कॉलम्स को इंटरचेंज नहीं कर रही? What is about this second property? अगर आपके पास, ठीक है, ट्रांसपोज अगर आप ले लें किसी भी डिटरमिनेंट का या किसी भी मैट्रिक्स का, उसकी रोज कॉलम्स बन जाएंगी ना?
यस सर.
इनफैक्ट आप जो ए मैट्रिक्स पे रो ऑपरेशंस लगा रहे हो वही ए ट्रांसपोज पे इनफैक्ट कॉलम ऑपरेशंस लग रहे हैं ना? सो दीज टू थिंग्स आर बेसिकली जब में हम कॉलम्स या रोज की बात करते हैं तो that is basically true by keeping this in mind, because if you have a matrix A, its transpose is what? You are interchanging rows, you are converting rows into columns. So for determinants, all these things are basically true for columns as well, because determinant of A transpose is equal to determinant of A. So these are a couple of properties. What is time now? Time क्या हुआ?
बस कर दे, आज काफी नॉलेज मिल गई है.
10 मिनट वैसे रह गए लेकिन सर काफी पढ़ाया.
दिमाग फ्राई हो गया आज.
वही यार, वो पहले इस वाली चीजें तो हमने प्रीवियस लेक्चर में पढ़ी थी. एक दो प्रॉपर्टीज और करते हैं, बाकी प्रॉपर्टीज हम नेक्स्ट लेक्चर में. These are very simple properties. You just have to remember them. You have to keep them in mind while working with determinants. Another very interesting property is that fourth है या fifth है जो भी. If you have A11 plus B11, A12 plus B12, A13 plus B13, फिर आपके पास यहाँ पे है A21, A22, A23, A31, A32, and A33. So in a first row, you have sum of two values in this determinant. in this determinant, the first row is sum of two different values, but the remaining two rows are normal. You can separate these two determinants by taking first entry, and first entry along with the second two rows. And then again, another determinant with the second entry, and second entry. So you can write it in this way: A11, A12, A13, A21, A22, A23, A31, A32, A33, plus determinant of B11, B12, B13, and then A21, A22, A23, and then A31, A32, and A33. Okay? For example, अगर हमारे पास EG अगर आप देखें यहाँ पे एक determinant है 2, maybe 2, 4, and 6, ठीक है? और यहाँ पे whatever the entries are here, we don't know. So we can split this determinant into two different determinants. For example, अब इसको हम पे 1 लिख लें, यहाँ पे 2 लिख लें, यहाँ पे 3 लिख लें, which is आप इसको लिख लें 1 + 1, 2 + 2, 3 + 3, or any other thing. You can write as well 0 + 2, 2 + 2, and 4 + 2. Okay, you can write in this way, and then you can separate this determinant into two determinants by writing first entry 0, 2, 4 here, and then 2, 2, 2 here. You can separate them. अब यहाँ पे देखें, अगर आपके पास यहाँ पे 2, 2, 2 है, ठीक है, और यहाँ पे 3, 5, 7 है, तो यहाँ पे आपने 2, 2, 2 लिखा, यहाँ पे आपने 3, 5, 7 लिखा, यहाँ पे आपने अगेन 2, 2, 2 लिखा, 3, 5, 7 लिखा, यहाँ पे 2, 2, 2 लिखा, यहाँ पे 3, 5, 7 लिखा, ठीक है? अब by using the third or fourth property, you can immediately say that this determinant is 0. Why?
वो जो हमने प्रॉपर्टी पढ़ी थी कि आइडेंटिकल रोज तो
two rows identical हैं, इसका
जीरो
determinant
रो बन जाएगी.
you can only try to find the determinant of this matrix. Okay, so this is one of the property in order to simplify the determinants. The rest of the properties we'll discuss in the next lecture. Now, if you have any question, you can ask. No question? There's a question in the chat window. Someone has written. What's this app? Okay, if you guys don't have any question, let's end this meeting. We'll meet maybe inshallah next lecture. You have a quiz in the next lecture as well. Okay, I have sent you the topics for the quiz as well. Okay then, thank you very much. Take care. Bye.
Offers.